Everyone. Benjamin, a Ph.D. student from the University of Oklahoma, and with my co-PI, Dr. Monique Gennady, and my supervisor, Dr. Shreya Vamaganti. So I'll be beginning. So with the course, with the outline, going through the backgrounds, objectives, methodology, results and discussions, and end up with the conclusions and future work. Okay. So as we all know, polymer concrete is an advanced composite material which was established in the 1970s, where the traditional cementitious binder is fully replaced with a polymer resin. So alongside, we have a polymer resin, and we have a hardener. So the polymer resin and the hardener is actually going to ignite the polymerization chains in the monomers. And we have a filler or aggregate. It's being subjected to a standard mixer. Then you get your polymer concrete. So polymer concrete actually use more advantages as it has a rapid curing due to the polymerization existing between the polymerization monomers between the hardness and the polymer resin. And it also has a higher durability as it cures very fast, and also it enhances a high good performance. It has a high strength as compared to normal cementitious concrete, and also has a high bonding as it gives a very good adhesion to pre-existing concrete materials. So we have some polymer concrete applications here where it serves as a very good work for preppers. Yeah, so in this case, since it has a very good high bonding performance, it gives a very good adhesion to the pre-existing concrete. And it also used in bridge deck overlays where it serves as a waterproofing membrane to avoid chemical attacks or chemical ingresses. And it is also used in precast element for transportation due to its lightweight. And finally, it's mostly used in bridge deck joint closures to at least give an adhesion between the bridge slabs. And actually, polymer concrete is way beyond this potential because it could be used in massive infrastructure buildings, but here's a problem. We do not have specification guidelines to actually lead builders or engineers or designers to actually produce a very large infrastructure. So as a result, our main objective is actually to generate a design guideline or a specification guidelines for all we engineers to actually realize the full potential of polymer concrete. And we are also gathering some documentations to be able to issue this command. So in this approach, we establish a motivation from Ashby chart. So an Ashby chart is a clear representation of a bubble visualization of materials, being it composite materials, polymer, or what have you, to give the mechanical performances depending on its density or weight. So as a result, we're using this framework through a data-driven approach to actually map the binder to aggregate ratio to its mechanical performance. So you're actually relating a micro-scale chemistry binder to a mega scale performance, actually. So we have an attribute chart representation here. So it's actually like we have a mother bubble. So we could see red, yellow, blues, and somehow green. So the transparent ones or the translucent ones are actually the mother bubble, and it enhances or houses the subset bubbles, which are actually the elements which exist within each mother bubble. So we're actually concentrating in polymers, which is our goal as engineers and civil engineers, where we want to actually establish how to use more of polymer concrete. So I'll be running you through to our methodology of how we're going to obtain this Ashby chart. So before I start, we actually extracted data based on the ACI 548 design guideline. They actually emphasized on these four polymer resins, which are epoxy, polyester, vinyl ester, and mesacrylate resin. So along with its specified initiator or hardness, which are the polyamide, the cobalt, actoate, and Norox, and benzoyl peroxide. So in this case, we have our subset materials to be aggregates or fillers. So you can have polymer concrete with resin, or aggregate, or a polymer concrete with resin of fillers. So these are the subset data, and these are the mother bubbles. And actually, we are focusing on the four main mechanical performances, which are compressive strength, flexural strength, split tensile strength, and elastic modulus. So in preparing this data, we actually used 6 main processes in actually to establish an Ashby chart for this goal. So we actually used a MATLAB code-based environment to actually deduce steps so we could just extract this Ashby chart. So I'll be running you through the process. So actually segregated the mechanical performances, which are the compressive strength, the flexural strength, split tensile strength, and the elastic modulus for each resin with its fillers or aggregates. And I had to segregate the mother bubble and the subset bubble, as I initially said, which are the resin types, epoxy, polyester, metal methacrylate, and vinyl ester. And the subset data, which are the aggregates or fillers. And actually sampled the data, where I actually clamped the data to get, I needed a reasonable or a realistic the binder to aggregate ratio of 0.1 to 0.6, as we normally build within those ranges. And actually went through the covariance ellipse for subset data, converse Hall boundaries, and the elliptical envelope to finally get the Ashby chart you see beneath there. So I'll be going through each of them. So as I said, I actually segregated the data into a compressive data, flexural data, tensile data, and elastic modulus data, as I initially said. And also did the material selection by separating the mother bubbles from the subset data. And actually clamped the data from 0.1 to 0.6 because actually we need a composite material. So anything beyond 0.6 is actually going to be a highly resin-dominated material. But we are more interested in the composite material to see how there's going to get the balance between the polymer and actually the aggregate. So in the covariance ellipse, so I actually had the data of each subset data, which I initially started with. So I had the data plots being plotted here, so you can see, and I segregated them into each respective assignment. So we have the conventional aggregate, the silica fume, and the fly ash, silica sand, and fly ash. So I actually use this one to elaborate for just epoxy resin for a compressive strength data. So the subset data for the epoxy resin was conventional aggregate, silica fume, and resin, and fly ash, and silica sand, and fly ash. So we have all these data here, and we can't actually say that these are actually the real data of, let's say, conventional aggregates, the real data of silica fume. We had to actually fit the data by using the covariance from statistics to actually see how the data is being covariated between the y-axis and x-axis. So the spread between the y-axis, you get these envelopes here, where this envelope symbolizes a covariance with an ellipse, which is actually fitting the data within each boundary. So we have a final ellipse from conventional aggregates for silica fume, and for fly ash, and silica sand. So these are the covariance fit data for each subset data. And as we all know, I initially said that you have to enhance the subset data, which is the mother ellipse, which is the epoxy, which we are yet to enhance the whole subset data into a one union. So we have the convex boundary, which is actually bounding the ellipse, to actually see that there is no data being extrapolated aside the boundary. So we're actually trying to draw a polygon around the data set to see it fits within the boundary we are actually saying, which is the convex hull. So we have the previous data here, so we just fit it with a polygon. So you could see everything is being enhanced in this polygon here, and we just finally draw our final ellipse. So we have it here, which is the boundary type. And an Ashby chart is actually not a polygon, it's actually a bubble visualization. So as such, with this polygon being drawn, or the contour being drawn around this, the subscribed epoxy, you're going to draw out an outscribed ellipse to actually enhance this one and just disappear the boundary. So the boundary is actually giving us how the ellipse is going to hover around this data. So actually, we use this equation, which was actually the minimum enclosing ellipse. So it actually finds the center of all the data, which is C, and actually draws the circle, which is the cos theta, and the sine theta. It draws the circle. But the circle actually becomes big, so you actually reduce the size of it so that it doesn't bloat away. It falls within the encompassed data you actually want. So finally, the polygon we had, now we have the ellipse being housing our subset data. So this is an encased and assigned to us epoxy resin. So we have an epoxy resin with the subset data and aligned with your binder to aggregate ratio and with your compressive strength. So we did the same for the subsequent resins, which are polyester, vinyl ester, and metal methacrylate, as we have here. So in our results and discussion, we are able to actually yield a compressive strength data. So with this motivation from Ashby chart, we've actually used the MATLAB to actually get the compressive strength data for a polymer concrete. So provided a builder wants to construct, fabricate a polymer concrete with a binder to aggregate ratio of 0.4 and is interested in using a vinyl ester polymer resin and with a subset data of, let's say, fly ash. So we have the fly ash here, which is being a subset of the vinyl ester. The vinyl ester, as in the legend, it says is green, and the subset data for fly ash is actually green, which is on the top right. So you match your binder to aggregate ratio, which is 0.4, and you just look on your y-axis true mapping, and you get a range of 70 plus or minus 10 megapascal. So with this, you actually know what you're working for, and it makes it easy to actually design. So this data was actually a scattered data, and now it looks highly visualized and makes it easy to actually see what you're working out for. So this is for compressive strength. Subsequently, we did it for the flexural strength, as you could see how it's more horizontally orientated. So we have the polyester, metal methacrylate, and the vinyl ester. So just as in the compressive strength data, you just map and also get your flexural strength data in megapascal. And the same applies to split tensile strength, the same mapping. And we finalized on the elastic modulus. Yeah. So actually, we actually did some try and errors to see how what we are doing is actually accurate. So from the ACI 548, which had some design ranges for compressive strength, we actually mapped it through this and actually realized that we are having the same thing. So this actually makes it more simple than seeing the actual ranges, which also discourages engineers and builders to actually rely on polymer concrete for large infrastructures. Thank you very much. And in conclusion, I would actually say that the Ashby chart has really helped, where it's converted a scattered data into a highly and a well-visualized data to actually make mapping simple. And also, it makes it simple in the second case that you're actually relating a micro-scale binder chemistry by the binder to aggregate ratio to actually see what is going on in the compressive strength. And also, it allows you to know which resin or polymer binder resin actually performed the best. And in our future works, we're actually trying to implement on using machine learning to actually learn on the data, because we would want to maybe build a hybrid system to want to see what is going to be the compressive strength if I'm to use epoxy with some portions of vinyl ester and some aggregate. What am I supposed to get? So in our future work, we're actually elaborating on using machine learning to actually enhance our study. I'd like to thank our sponsors, NEx. They've been wonderful so much with their support, and the other sponsors and ACI for this platform. And I would like to thank my supervisor, Dr. Vamaganti, who has been really helpful, and my co-PI, Dr. Munib Gennady, and my lab mates who made this thing successful. It wasn't a one-person job, it was a teamwork, so I'd like to thank them as well. Thank you very much.